Hello there, AP Stats students, and welcome to the most important lesson of the class. Today, you're going to learn about significance tests. Significance tests are the absolute backbone of inference. They're used all the time in statistics. Yes, confidence intervals are also part of inference, but the significance test is probably just the most widely used thing we do with statistics. So really important that you understand how to do it and the logic and reasoning behind it, because there's a lot of logic involved here. So just because you do the calculation right, if you can't make the correct conclusion from that calculation, well, then you've messed up. So it's doing the calculation correctly and making the correct conclusion. So let's take a look. But real quick, before we actually get into significance testing, I'm going to review confidence intervals. So try this problem real quick. So we have a study, 36 job hunters. Average time to find a new job, 5.9 months. We're going to assume we know the population standard deviation of 0.8, which again, in reality, we probably would not know, but we'll talk about how to handle that later. For now, we're going to just pretend. Okay, let's find a 95% confidence interval. All right, first of all, make sure you validate your calculation. Okay, so there are at least 360 job hunters out there. In the population. So we may safely use our standard deviation formula. Okay, that's one of our criteria. Right. Also, we need to know that the data is unbiased, right? That we have good data. It doesn't really say, so we're going to have to assume the data came from an SRS. If not, calculation could be invalid. Okay, so something like that. And lastly, we're going to be using our z-scores, right? So we're going to be using normality. We will, again, at this point, just invoke central limit theorem. We'll talk more about that later. Technically, 40 is the number that we're going to use, not 36, but for now, let's just pretend, because it's a can of worms that we're going to just kind of kick down the road. So don't do this on the AP exam. On the AP exam, by then you'll understand a little bit better. So we'll just say the sampling distribution of X bar. I'm going to use the word should instead of will be, because again, we didn't hit the 40. So we'll say should be approximately normal. Due to the central limit theorem. Okay, so we've now validated our calculation. Again, we have kind of some little assumption there, and the normality is a little bit unsure, but we're just talking about it now. We'll get into those things a little bit more in future lessons. Okay, so now do our confidence interval. So we're going to take our X bar, right, plus or minus a margin of error. And the margin of error is, of course, our critical value multiplied by the standard deviation of our statistic, also known as our standard error. Okay, so X bar is 5.9. Our critical value we can look up on our table or use our calculator, right? Because again, the 95% confidence, and the 0.8 is given and 36 is given. So we plug that in to our formula, and here's what we should get. Okay, and then, guess I didn't write it out. Please write a complete sentence answer. So we are 95% confident that the true mean, I'll write it down here. The true mean time is between, you really should say true mean time of job hunters, blah, blah, blah. But I don't want to take forever here. And let me also refresh your memory on how to do it on your calculator. Okay, so if we go under distribution, we should somewhere, oh no, sorry, not distribution. We go under calculate. And there we are, calculate tests. This is a z interval, so number 7. Okay, in this case we have stats, so I choose stats. Okay, sigma is said to be 0.8, X bar is said to be 5.9, N is 36, and a confidence of 95. So here's how you do it on your calculator, and voila. There we go. 5.6387 and 6.1613 months. Okay, and there you go. So hopefully these are easy. Okay, little follow-up. What was the margin of error? Well, the margin of error was our z star times sigma divided by the square root of n. Oops. Which, of course, we have right there. Right, it's the amount that we are adding and subtracting to make sure that we capture the 95% confidence. Okay. Now, what if I wanted to reduce my margin of error to 0.15? Well, obviously, I'm going to have to increase my sample, and we can calculate the exact sample size required, right? Because we just take our margin of error there, and we set it less than or equal to 0.15, and solving, we should get 110. Okay, so here's the work for that. Our margin of error. Okay, and we plug in our z star, we plug in 0.8 for our sigma, and we solve for n. Let's, I guess, refresh your memory on finding our z star with our calculator. Okay, remember you can find it from your table, but for your calculator, you can go into the inverse normal. Okay, and remember a 95% confidence. It's a center section of 0.95. So that means over here you have 2.5%, and over here you have 2.5%. Okay, so if you want this value, you need 97.5% below, or you can just find this value and take the absolute value of it, right? Either way. Okay, so there is your z star. Okay, so you going to take that value for z star, approximately 1.96, and 0.8 over square root of n less than or equal to 0.15. Okay, solving that. And there we go. So again, remember, I cannot have a sample size of 109 point whatever, so I have to go up to a sample size of 110. And again, write this as a complete sentence answer. You would need a sample size of at least 110 to reduce the margin of error to 0.15. Okay, so that was just a quick review of confidence intervals. And again, those are quite important. You will definitely be doing those on the AP test. But an even bigger part of inference is the significance test. Okay, so let's start talking about these two things. Confidence intervals. Okay, we're going to use those when our goal is just to estimate something, right? We're estimating a parameter and we're like, okay, we're 95% confident it's in this window. Nothing wrong with that. But sometimes we want to go further than that, okay? And that's when we use a significance test. Okay, the significance test is trying to show, illustrate, refute a claim. So someone might be making a claim that doesn't really matter. Let's say the average high schooler spends 4 hours a night playing video games or something like that. You go, I'm not so sure about that. Let's make a bet, you know? And so then to answer the question, you'd have to go out and collect valid data. And then you would look at that data, and that data would give evidence one way to hopefully, you know, win the bet for you. But we'll see how it works here in just a second. All right, so to do this significance test, first you start with your null hypothesis. Okay, the null hypothesis is exactly that. Think about the word null, nothing, right? It's stating that there's nothing here. Things are what you expect. Things are in line with everything else, with the claim, okay? So when the null hypothesis is true, whatever data you observe is simply due to random chance, right? So it's just random variation that we observe in the data, so our null hypothesis is true. There's nothing here, okay? Now, you can go around writing things in complete sentences and say the null hypothesis is blah, blah, blah. Or you can use mathematical notation. So instead of saying the null hypothesis, you can write H with a subscript of 0, or in other words, H naught. Again, H, nothing is here, null. And the null hypothesis will always, always, always be an equality, right? Equality. So right now we're going to work with means. So our null hypothesis will always be that the true mean, the population parameter for mean, is equal to some number. Okay, this will be some number over here. Okay, very important you understand, null hypothesis will always be an equation, an equal sign, an equality. Okay. Now, you also will need an alternative to that. Okay, so the alternative hypothesis is this is too high, too low, or it's simply different, right? Those are your three options. Okay, and again, this is like your bet. Maybe somebody claims, oh yeah, average high schooler plays video games for 4 hours each night, and you go, no way, that's too high. I don't think so. I think it's less than that. Well, there's your bet. Or you could have said, no way, that's way too low. I think the true value is much higher. Well, then now you're making that bet. Okay. Or you could say, you know what, that just doesn't sound right to me. I don't believe it. Then you're making this bet, right? So those are your alternative hypothesis. And you're going to put, again, H and then subscript A, standing for alternative hypothesis. All right, now it can't be all three, right? It's only going to be one of these three, and you have to read the question to figure out which one you're working with. All right, So this is what I was mentioning earlier. The logic, the reasoning behind this is really important to understand. Okay, so the whole calculation is based on assuming that the null hypothesis is true, right? We assume that it's true, and then we do the whole calculation assuming that it's true, okay? And then if that data, if that result is super rare, assuming that the null hypothesis is true, well, now you have evidence that the null hypothesis is not true, right? That's the whole logic behind the test. Pretty simple, really, but for some reason, a lot of students get confused by that. Okay, so the whole idea here is we're saying, I have a null hypothesis. I now go out and collect data. Notice that the null hypothesis would come first. Then you would, hey, I don't think that's right. Have your little bet, your argument, whatever. Then you go out and collect your data. And if the data is really far off from that null hypothesis, you go, I don't think the null hypothesis is true. And you reject it. It's that simple. All right, some vocabulary. So p-value. The p-value is just the probability of attaining a result as rare as you got or more rare, right? At that extreme or more extreme. Okay, and again, it's going to be based on, are you looking for evidence greater than? Are you looking for evidence less than? Or are you doing a two-tail, meaning the not equal to? So it's one of those three things as your alternative. So your alternative hypothesis is going to dictate if you're looking right tail, left tail, or the two-tailed, okay? And then as I already mentioned, the p-value is the strength of your evidence. So the smaller the p-value is, the more evidence you have to refute or reject your null hypothesis. All right, so again, more vocabulary. When we have that small p-value, we say we have a statistically significant result. Okay? It means we have evidence against the null hypothesis. We have enough evidence to reject it, to overturn it, to refute it. Okay? And the reason we have these terms is because a lot of students, they want to say, we have proven the null hypothesis false, or we've proven it true, which you never, ever, ever do, because it's never a guarantee, right? You get a p-value and, oh yeah, this is really rare. Well, really rare doesn't mean impossible. So a lot of students use that word prove or proven, right? And that's wrong. If you use that, you will lose a ton of points. Do not use that word. That's why we have this terminology. We say, oh, it's statistically significant. That means we have enough evidence, but it's not a guarantee, right? Having evidence is different than a guarantee. It's different than I've proven, right? Mathematically, when you say you've proven something, that's guaranteed. That's the end of it. It's done. There's no more argument, okay? In a significance test, you have evidence, but it's not a guarantee. So please understand that. All right. Now, how much evidence do we require? Well, the cutoff for the amount of evidence that we need is alpha, okay? So that little Greek letter there. And I think I mentioned this a little bit earlier, right? Alpha is, of course, when we were talking about this little diagram here, right? We had our confidence, okay? And over here we said, oh, well, this is going to be 1 minus the confidence divided by 2, and so is this, right? And then we're saying, oh, well, rather than writing 1 minus the confidence, we could just call it, alpha. So there you go. Okay. So basically what we do is we do our calculation, we get our p-value, and we compare it to alpha. It's that simple. When our p-value is less than alpha, we say, that was rare, very rare. It's statistically significant. It's rare enough to refute or overturn or reject the null hypothesis in favor of the alternative, okay? The most common alpha is going to be 5%. Okay. And again, when we say something is statistically significant, we're simply saying it's not likely to happen due to random chance. It could still be random chance, though. That's why, again, we don't say guaranteed or proven. We say it's significant. Okay. And here's a phrase you're going to use a lot. When you get a p-value greater than your alpha, you're going to say, well, I don't have enough evidence to reject. I fail to reject the null hypothesis. And again, that doesn't mean the null hypothesis is true. It just means you couldn't refute it. You couldn't overturn it. All right, let's try a problem. All right, so we have a report that says assistant professors' average salary should be more than $42,000. Somebody's claiming that. Somebody else obviously would say, I don't think so, right? And now here's our argument. So we stop there, okay? I know that when you're doing the problem, they have to give you all the information in that problem. But remember, it would have started with a null hypothesis and then a claim, one way or the other, an argument, okay? So don't get mixed up with all of this other information that came after. Right there, they just told you your null hypothesis. Well, they told you your alternative, which tells you your null hypothesis, okay? So the alternative hypothesis is more than $42,000. Okay, well, that sets the null. The null hypothesis then has to be an equation, an equality, and it has to be the same number. Okay, so this is the argument that occurred. Somebody said, oh yeah, the mean is 42,000, and then some other researcher said, no, the mean is more than 42,000. There's the argument, the null and alternative hypothesis. Then they go out and collect the data, right? And again, this is the confusing part, because in order to do the problem, you need all this info, right? You don't understand that it actually happened in steps. So just do that step. Now, here's the data. Okay, they went out, they got a sample of 30. There's the mean of the sample. Here's the level of evidence they agreed on to solve, to resolve their dispute. And there is the standard deviation of the population. Again, we're playing make-believe that we have that. Okay, let's validate the calculation before we actually do it. So remember, we need to have a population at least 10 times the size of the sample in order to use our standard deviation formula. There's definitely going to be at least 300 assistant professors out there. So there are at least 300 assistant professors in the population, allowing the use of the standard deviation formula. Okay. All right, what else do we need? Well, we need good unbiased data. It just says a sample. It doesn't say what type of sample, so assume the data was collected by an SRS. If not, it could invalidate our results. Right? In other words, it could be that during this argument, one of them kind of cheated when they collected their data and introduced bias to try to help their cause, right? It's not unheard of. Okay, and lastly, we need normality, right? So again, 30 isn't It's not quite 40, but we're going to get into that later. So we're just going to say assume, or we'll just say a sample of 30 is large enough due to central limit theorem, even though in the future we're going to make that number 40, just for now. So we should have approximate normality of the sampling distribution of x bar due to the central limit theorem Okay, so now let's actually do our calculation. All right, so it's hard to get this whole thing on the screen. I'm gonna go ahead and just turn the page here. Oh, perfect. So that's what we already covered. Now, sometimes students get hung up on the claim. Sometimes the claim will be the null hypothesis. Sometimes the claim will be the alternative. Just think about it. It's an argument. One person is going to make a claim on one direction and the other person is going to make a claim for the other. Okay, so even though the problem only said, here's the claim, right? There's somebody else who had this idea as well. So don't worry about which one the claim is, right? Just think there's a null and there's an alternative. Now you can, I didn't mention this yet, you can compare z's, right? You can say, how far do I have to get, like how many standard deviations do I have to be above the mean in order to hit that level of evidence where there's only 5%, right? This was a one-sided, so the alpha here, right? Where there's 5% all above, right? Because our alternative was greater than, so it's 95% over here, 5% over there. Right? I gotta be past this line in order to say I have enough evidence. So you could find the z star that matches this cutoff and just compare your z. The problem is that's a little bit less informative than getting a p-value, right? Just saying that my z didn't quite make it or my z did make it, well, by, how much were we off probability-wise, right? So that's kind of a more old school technique. Now that we can find probabilities quickly and easily, we typically give those probabilities, okay? So, and the way to get that z star, of course, is to use your inverse norm. So I'll just show you that again. Distribution menu, inverse norm, 0.95. There's your z star. And again, because that's 0.95 all to the left. This is not a two-tailed alternative. All right, so calculating your actual z, right? Here's our x bar. There's our parameter, and there's the standard deviation. So we get this z-score, and you can see this z-score is not extreme enough, right? It's over here somewhere, right? We didn't hit the necessary number of standard deviations. But the more informative thing to do is look at the p-value associated with that z-score, and you can see random chance said, we could get something this extreme or even more extreme a little over 9% of the time. So when that happens and our alpha was 5%, we're saying we don't have quite enough evidence. We do have some evidence, it's just not enough, right? So the conclusion we didn't have enough evidence, right? Because our p was greater than our alpha. Okay, so we didn't have enough evidence. So the conclusion is we cannot support the claim that assistant professors make more than $42,000 per year on average. Okay, or we could say fail to reject the null hypothesis. Right? We cannot overturn that they do make $42,000 per year, right? You could say it either way, because again, there's two sides to the argument, and you can Just basically say which side you're supporting, which side won. And there you go. So hopefully that made sense. We're going to do one more example because the first example there was a one-tailed example. Let's try a two-tailed example. All right. So I make a claim that my students have an average GPA of 4.0. Okay. And we would stop there. There's your null hypothesis equals, right? So in this case, the claim is the null hypothesis. So you would say H naught mu equals 4. Okay, now somebody would make an argument with me, okay? And we have to continue reading to see if that argument is, I think it's less, I think it's more, or I just think it's not 4. Random sample, blah, 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 blah. Is there enough evidence to refute the claim at the 5%? Okay, so there is the alternative. Notice it doesn't say we think more. It doesn't say we argue that it's less. We just say, can we refute it? So that's why this one is a two-tailed test. You're saying it's not 4. Okay, you cannot look at the sample. Don't look at the 3.9. Is 3.9 less than 4? Sure is. So a ton of students put less than here. But there's nothing in the problem telling you that we're suspecting that it is less than or arguing for the less than. You can't look at the data to set this up because, again, this should have been set up before the data was ever collected. So let me stress that again. You cannot look at the data to set up your alternative because the alternative should have been set before the data was collected. This is just one of those things where we got to give you all the information in order to do the problem. So we give it all at once. So don't look at that to set up that. That's what we're saying. Okay, so let's validate our calculation. Our sample is 25. Do I have 250 AP Stat students? Well, not this year, but over the years, yeah, I've had a lot more than that. So the population of Mr. Crow's AP Stat students is at least 250, allowing the safe use of the standard deviation formula. Okay, now we need good unbiased data. It just says a random sample, but we don't know what method was used, but it should be fine if it was a random sample. So we'll say the data came from a random sample, so it should be unbiased. Okay. And lastly, we need normality. Again, 25 is not 40, but we're not going to go there yet. So just say we should have approximate normality of the sampling distribution of X bar due to the central limit theorem. Okay, so we validated things. We'll get more into that again at a future time. So now we have to actually do our calculation, right? So let's turn the page so I have a little more room. Okay. I'm just gonna actually, we won't do the whole drawing thing again. Well, no, let's do the drawing thing. I have some blank space here, so we'll do this drawing. All right, so in this case, our alpha was 5%, but it was two-tailed, right? So we have that, okay? Which means we're actually looking at what we would consider to be a 95% confidence interval, okay? So So your Z star is right there. Okay, and there's also a negative one over here. So we're saying if we land outside of these cutoffs, we have a rare outcome. If we're landing inside, it's not quite rare enough. That's what we're saying. So you could actually just do the 95% confidence interval and ask if your X bar landed inside or outside of it, right? So you could do that. A lot of people actually do that. But again, the p-value is a little more informative. So let's do that. So getting our Z, you see we get negative 2.5. So we're over here, right? Negative 2.5 is over here, which tells me I have a very rare result, right? Rare enough that I'm landing in the rejection region, right? I'm inside the alpha. So I'm going to be rejecting here. Again, I can compare the Z with the Z stars. I could compare p-value with alpha. Or I could get these in terms of X bar, right? I could do a quick confidence interval. So let's actually do that just to show you. So do a Z interval. Okay, again, we have stats and not the actual data. If we had the data, we would say data, it's in list 1, and then it could just do the whole thing. Okay, that was 0.2. X bar was 3.9. And it was 25. Okay, so if we get a number in between these two, we'd say, oh, we don't have enough evidence. But if we're outside of those two, then we'd have it. So 4.0 is outside of that, right? So we would have enough evidence. Okay, the other way to do it would be, well, let's just stop there. I don't want to confuse you too much. So getting our p-value. Okay, this is something we've done in the past. Hopefully you can remember. Since it's two-tailed, right, we're going to do less than that. We're going to look at this area right over here, but we also have to accept the equivalent on the other side. So we look up this side and we get the 0.0062. We double it, so there's our p-value. So the p-value is smaller than alpha, as we already knew it was going to be, right, from the drawing I made. So we have evidence to overturn my claim. So the conclusion, it appears that my claim is likely false. It looks like my AP Stat students do not have an average GPA of 4.0. Okay, and it's that simple. Let me show you how to do this bit on the calculator as well. So you may have noticed in the test menu, there's also something called a z-test. Hard to read that. There's also something called a z-test. So I could choose that and enter all the information. In this case, the null hypothesis was 4, and looks good. And there's my alternative, yeah. And there you go. Gives you your z and your p-value, okay? You could also, of course, draw it. If you notice that as a choice, come down here and draw it. Looks like I have another graph on there. Oh, gotta do it again, sorry. Okay, and this is the drawing that I kind of made. And it's really even hard. It's so small, it's hard to see, but there's a little shading right there and right there, corresponding to that area, split in half, right? So anyway, hopefully that makes sense. Please spend a lot of quality time with this, because as I mentioned, it's a really important concept. We're going to use it a lot. So you want to not only know how to calculate it, you also need to understand the reasoning and the logic behind it. All right, thanks for tuning in.